thinking about or bothering you or don't make sense? Okay, thought I'd check. So we're going to continue on with momentum and impulse and their changes. Impulse is a change in momentum. And get into energy today. We'll do some more collisions and introduce some forms of energy. A brief recap. We had from Newton's second law that relationship between acceleration, force, and mass. And we know acceleration was the change in velocity with time. So when you cross multiply, you get this relationship between the product of force and time, impulse, and how the velocity changes, which is a change in momentum. So that came right out of Newton's second law. Newton's third law is when between an action-reaction pair, the force is the same, equal and opposite. So we've done this before. If you have something with small mass, you get a big acceleration, and something with a big mass, a little acceleration. Now, if you, well, do it this way. Big mass, acceleration is a change in velocity with time. Can you see where this is headed? Here's our change in momentum. If you multiply both sides by the denominator, t, in the middle, you get change in momentum. Change in momentum is force times the time, which is the impulse. So what that tells me is what we've been talking about. Just thought presenting it this way might help some of you if you weren't getting it. You apply a force. Let's put it over here. You apply a force, it causes a change in velocity. You apply an impulse, you get a change in momentum. We were doing some elastic and inelastic collisions and conserving momentum. Let's do some more. Here's carts. They're tied together with a different spring. There's no Velcro on this one. So they should fly apart because they're going to feel equal and opposite forces. How will their velocities compare after they spring apart? Be the same? Oh, excellent. They'll be the same speed, scalar magnitude, but they'll be technically different velocities because one's going one way and one's going the other. So they'll be heading out with the same speed but opposite directions. Again, we could figure that out without ever having to do the experiment. Don't worry, we'll do it. Again, momentum before is momentum after. So the momentum before is, since they have the same mass, mv1 plus m2, I guess initially. That's not, usually represents initial. If you want like to do a little I, you can do whatever you want. mv1 final plus mv2 final. So they both have momentum before, they both have momentum after. Now, this is kind of generic. This is how I like to start and look at these, especially if you get confused. Now let's break them out. What's the momentum before the collision of the cart 1? 0. That was easy. 0, 0. We did this. So the total momentum after they separate must be 0. But they're moving. This one will go to the right. This one will be going to the left. So one's negative, one's positive. The only way for that to be 0, with them being the same masses, is if they're going the same speed. Let's see if it works today. They look like they're about the same speed to me. They hit the ends at about the same time, and they come back together in the middle. But of course, these have a spring, so they keep bouncing. What's the total momentum right now? Now? Now. It's always 0. Since we started at 0, it's still 0. Now, if somebody came along, some external force, and goes, that would add momentum to the system, and now it wouldn't be 0. But if you account for that, the total is still conserved. It's just we didn't start with it. Let's bounce some other things off each other. We started doing that. You guys like this one. Since they're the same mass, boink, dead stop. Because they have the same mass. So his momentum is completely transferred to him. When it's lighter, less mass, psh. How would you know how they're going to react? Let's do it again. Let's say this is, if this is M, we'll say it's cart 1. Then let's say this one is twice as massive, because it's close enough. So afterwards, we get these final velocities. Whoops. Twice as massive. All right, where's the momentum before the collision? Say this one's coming at it. So like now, before the collision. This one's not moving. So that momentum is 0. And we have 2 mv, whatever velocity is coming in at. So that has to be the total after. You saw that both of them were moving. So how do the velocities have to adjust with those masses to make this possible? These have to add up to 2 mv. And in this case, they both move in the same direction after the collision. They're both going this way. So the magnitude of their momentum add. I know you don't know the numbers exactly, but can you say what happens to this one? It increases, and that one will be less and smaller than what it started with. We saw that last time too. Now that you know what you're looking for, just compare the speed of that guy. It slows down. Yeah, both of their velocities changed after the collision. But again, their combined momentum stayed the same, because momentum's conserved. Even when it goes the other way. We'll run the small one in. So initially, this is all the momentum. This momentum's 0. So the momentum is just, that's 0. It's mv. So the total afterwards has to be mv. They both end up moving, but in opposite directions. That kind of helps cancel their individual momentums to make the total less than it was before. Let's see. How fast should this guy be going? Is there any speed we could go? I'm winging this. When it runs into this one, where it would stop. Should we pick up the speed? I heard most people say, let's go faster. Let's see. Nope, still bounced. Nope, still bounced. How about super duper slow? Doesn't appear to. And so, boom. Nope. If they're both moving, maybe. Let's see if this guy's coming in faster. And he's going pretty slow. Nope. The idea here is the picture's incomplete. Not only are we transferring momentum and conserving momentum, energy is involved also. That also has to stay conserved in an elastic collision where they bounce off each other. They have motion. And we're getting to that. We'll do our couple inelastics. We did this one where they both had the same speed. If they have the same speed, they come together and stop. What now will happen? It's coming in. They'll stick together and move in unison. How do you do that? It just looks like this. They're both moving together with the same velocity because they're stuck together. So it's the same idea. So you got mass 1 times that final velocity plus mass 2 times that final velocity. You can just rewrite it simply like that. Inelastic, where they stick together. Or yeah. So initially, one of these is going to be 0. Make it on the right, number 2. So we have some total momentum as it's coming in of mv. We know the final has to be 2m some v. This one we can do. What is that going to be, the final velocity, relative to the initial? Half. Can you see that? In order to balance this equation, to keep it equal, to conserve momentum, this will have to go half the speed. So let's see. Send that one down. It's coming in at a certain speed. They stick, and they do slow down. It's not stark obvious. I don't have any meters out here for you to gauge. That's coming in. Can you at least tell it's slowing down? You now know that's half the velocity as it was coming in. It should work this way as well, because they're the same mass. They slow down. What if we do this one? They'll stick together. What will be different? Even slower? Yeah, the one coming in has the momentum. And before the collision, this one's moving, and it's half that mass. We could write that one. This time we'll just do, it's coming in like that. That one's not moving. Afterwards, it's the combined. So can you see that will have to, what is that? 2 over 2, so 3/2, 1.5 the mass times the final velocity. You could work that all out. Doesn't matter. Let's just see what it looks like. Come in. They collide inelastically. And yeah, that one's even more conspicuous that they slowed down. Could you tell? We'll go faster. Boom. You can go the other way. Now it's got more momentum total, so it doesn't slow down as much. Do that one again. The bigger one has the momentum, so you hardly see any slow down at all. It does a little, but not near as much as the other way. So anytime you have objects coming together, that's how you can figure out what their motion is going to be before or after, depending on which one you know, because you can use this conservation of momentum. If you look at all the momentum before and all the momentum after. So you rarely can win, you know, in football. You have somebody that's just huge, and then you got me. Just because they have so much more mass, if we tackle each other, you run in at each other at the same speed, you guys know I'm not going to win. They come in with more momentum because of that increased mass. So when we collide, that's like the big player hitting the puny player, and you end up going that way. Any questions on this stuff? I've had this out a while. It's time to finally do it. The thing. Boxing gloves. You would never hit the brick wall with your bare hand as hard as you could, right? Because it would stop too quickly. But you can nail it with this guy. I saw it at a garage sale. I had to get it. And why does that protect my hand? Physics answer now? It slows the time of impact, thus reducing the amount of force to stop my hand. You come in with so much momentum, whether you have the glove on or not. The glove doesn't weigh that much. So the momentum coming in initially is about the same. Then you collide with the wall, which has 0 momentum. Your change in momentum is mv to 0. So it's the same change in momentum, it's the same impulse either way. But if you do it quickly, without the glove, lots more force. With the glove, you can hit it as hard as you want. Now, many of you have seen these executive toys. Newton's cradle. What will happen when I lift one ball up and let go? It'll collide. They'll all collide with each other. The force is transmitted through. Momentum is transferred. And this one will come. They're all the same mass. So what speed do you expect this to come out with? And that's the classic. Works like a charm. It's just like the two carts where one, there's a dead stop. Transferred all this momentum. Because they're the same mass. So, what happens if I lift 2? Are you sure? Now it's 2 mv, the momentum coming in. What if this mass had twice the velocity? Could happen, right? According to conserve momentum, that could happen. But it doesn't. You get 2. But 1 could come out being twice as fast and have the same total momentum as the 2 going half as fast. But because energy is also conserved, this is the way it works. And 3, you know what will happen? 3. So, 4. We don't have 4 over here. What's going to happen now? These could go twice as fast, right? Because they have half the mass. That would conserve momentum. And maybe that's what happens. But it isn't. Four still come out.
That is so trippy.
Should we try 5? 5. All right. Now, just to blow your mind, how many will come out with 6? Who says 0? Well, there aren't any balls over here.
I say 0.
It's a trick question. They don't hit anything, so you could consider it 0 or 6. See? No, I'm just How many? If any of you played with those clacker toys, you know these things, they're the same mass. So as you go around, you can see how it dead stops at the bottom. Well, if I can hold it still, they collide. If you practice, this is easier with a larger one of these, but you can go up and down. You know, oh. Slow-mo, you know, they're boom, boom, boom. But because they have the same mass, they just rebound with the same velocity, and so they stay symmetric. All right, what if we do one on each side?
The other one on the other side.
So 2. All right, let's try 2 and 1. This is fun.
It'll be 2 on that side and then 1 on this side.
Let's try 3 and 2. Yeah, we'll do 3 and 1. I love collisions. So as weird and mysterious as this might seem to you, though, you can predict what's going to happen with conservation of momentum and conservation of energy. So let's talk about energy more. Chapter 7. So back with, I mentioned Émilie du Châtelet. It was in the 1700s. She did the experiment, dropping the ball. What's this oomph that happens? And she went and actually did the experiment. And they realized that oomph, my term, was it proportional to mv or was it proportional to mv squared? Well, long story short, they found out it was this. This one you recognize. This is momentum. This proportionality is related to energy. And some of you probably already know. Kinetic energy, we'll start with that one. Kinetic energy is exactly equal to 1/2 mv squared. They saw how far the dents were made and realized the faster it came in at, the energy it imparted, the work it did on the clay, changed by this factor squared instead of a linear relationship like this. So now we know that it's energy that determined that, the work done. Work, you hear all the time. Work is, oh, well, pause, Adam. So kinetic energy is energy associated with motion. Something has to be moving to have kinetic energy. If it's not moving, there is no kinetic energy. So, yeah, this is the work done on something to change its motion, the speed of it. Work is work. W, force times a distance. We've talked about you apply that force to make a change in acceleration. And that force acting over a certain amount of time applies an impulse. It changes the momentum. You've got that now. Well, when you apply that force for a certain amount of time, it's over a certain amount of distance. Think of it, when I push this, it gives. So that compression distance, or the crumple zone distance, while that force is applied during the collision itself, you cover a certain distance. Well, what do we call that force times that distance? We call it work. This is a way to transfer energy. I used to think, when I was a kid and student, of work as just another form of energy. I don't anymore. It just transforms it. It transfers energy from to different forms, or to change somebody's energy. And you know this. If you push on something over a distance, if I apply a force to this over this distance, what did I do to its kinetic energy? I changed it, and did it go up or down? Yeah, I increased it. What's its kinetic energy now? Nothing. And now, something greater. So I changed its kinetic energy by applying a force for a certain distance. I also applied that force for a certain amount of time. So I changed its momentum and its kinetic energy at the same time. Both things are happening. But momentum is this, and energy is proportional to this. Exactly that. So just think of work as a way to move energy around or change it. It's like a transition. Another form of energy you're probably familiar with already. Gravitational potential energy. GPE. That's the energy associated with position or location. As you move things around, you probably know this. Relative to the floor, this is up a certain height. So if I push it off the table, you know what happens, right? How did it get from here to there? Gravity. What acted on it specifically? Yeah, the earth pulling on it. The earth exerted a force on it. And that force was applied for that distance. It applied on it until the floor stopped it. So see, the earth just did work on the glove. Force times distance. What was the force on it? When it was falling, we could draw a free body diagram. Here's the glove. What's that force? 10's the acceleration times mass, Newton's second law. So mg, that's the force that the earth applied. So I'll put that in here. And how far did it fall? The height of the table, right? How high up it was relative to the floor. That's gravitational potential energy, mgh. So how am I going to get it back on the table? I have to do work on it. How much force should I apply to lift this? Equal and opposite to its, not mass, weight. Yeah, so mg, I have to apply mg upwards to counter its mg downwards. And then I can lift it, at a constant velocity if I want. Over this height, I just did work on it. How much? How much work did I just do? Yeah, force times distance. I applied a force of mg for the distance of height, mgh. So how much gravitational potential energy does it have right now relative to the floor? How much gravitational potential energy does it have relative to the floor? mgh. It's up here at a height. So this gravitational potential energy is the energy associated with position, relative. It's always relative to something. So if it's up this high, look at it. It has the potential to do something. So if I just, like we did, woo, there it goes. Now what's its gravitational potential energy? Yes, it's the obvious answer. 0. It's at the floor. It has no height, so it has no gravitational potential energy. So when I kick it now, it doesn't fall anywhere. Does that make sense?
So this only do position in
The vertical plane, in this, because this force is acting in the vertical direction. So yeah, gravitational potential. So yeah, it's vertical. Yeah, if I move this, what's its gravitational potential energy relative to the floor? mgh. What is it now? Yeah, so its potential energy didn't change. Gravity couldn't do any work on it because it didn't move at any distance. And here's one that students don't like. Sorry. It's different than what normal lingo. If I come over to the wall and I push on it, I'm exerting a force on the wall. Did I do work? If I pushed long enough, I'd start sweating. Did I do work? Yeah, in layman's terms, people would say yes. In science terms, absolutely not. Because work is a way to transfer energy, and I didn't make that move, so its kinetic energy didn't change. And I didn't move it up or down, so its gravitational potential energy didn't change. I didn't transfer any energy. I didn't move at any distance. So even though I exerted a force, if it doesn't make the thing move, in science, we say no work was done. Your book mentions the work kinetic energy theorem. We've actually already explained it. But it says the network, the network, yeah, I've always liked that. Thought that was funny, sorry. The combined work, because just like when you combine forces, you can have net forces. How would you get a net work? Well, you could have force 1 moving something a certain distance, plus force 2 moving in a certain distance, plus, you get the idea. So if you add up all those forces and distances trying to move an object, that gives a change in kinetic energy. That relationship is called the work kinetic energy theorem. We talked about theories in chapter 1, so that's our guiding understanding of the relationship that goes on here. I'll give you an example. And we're already halfway there. When I lift, okay, what's its kinetic energy? Right. What's its kinetic energy? Did its kinetic energy change from the beginning point to the end point? Yeah, no. In between it had some, but at the beginning and the end, its kinetic energy was 0. So its change in kinetic energy was 0. I have not changed its kinetic energy from beginning to end. If looking, overall, it doesn't have any kinetic energy now. So the work kinetic energy theorem says the net work done on that is 0. But you guys are thinking, whoa, you just did work on it, right? Yes, I did. I did work up on it, didn't I? I put force up, moved it up. I did work. There's one work. Who else was doing work on it? Gravity was trying to pull it back down for this over the same distance. So while I'm coming up, it's pulling down for the same distance. It acts on it the whole way up. That's what I was overcoming. They cancel. That's why the net work on it is 0. And we can see that because I have not changed its kinetic energy from beginning to end. So that also means in science, if I come up, if I start here, and I walk around and I climb up, I could go all the way around, back down, up here, onto here, and come back to this spot. My net work done on me is 0. Because look, I haven't changed my kinetic energy. I did it in the middle, but from beginning to the end, there's no end result. I went up at some point, and I came back down in another point. Just like this. Versus no ultimate change. That one can be, that's probably the most confusing for students. Does it make sense what I'm trying to say?
So you moved up and stayed up? Would your
Yes.
energy change?
No, that's like this. If I moved up and stayed up. So that's like starting down here.
Okay.
Not moving, so no kinetic energy. There. Worked better than I intended. Its kinetic energy is 0. So the net work done on it throughout that whole thing, the combined work is 0. If the kinetic energy hasn't changed from the beginning and now at the end, then absolutely. It has to be 0. Yeah, when it does change. This. While it's moving, even this, while it's moving, there's a change. This one, with friction, the work I do on this to accelerate it, a force, my hand, for a certain distance, there. So from here to there, I've changed its kinetic energy from 0 up to something. So if you're just looking right here, there was clearly a change. Same with this. If you're looking in the middle during the process. But then friction exerted a force to slow it down for another distance, applying force on it in the opposite direction. Work on it, I mean. And that work canceled the work I did on it because it's not moving again. Ultimately, there was no change in velocity from when I start out and when friction ends up. Yeah, it's kind of goes up, comes back down. Yes?
So if something is stopped, its network is 0?
If it stops. Well, it depends. Did it start? Stopped? Say something was already moving and it stops. Now there was a change in kinetic energy. The net work would not be 0. So you're driving your car, going along the highway. You need to stop. You slam on the brakes and you stop. Now there was work done, net work done on you because your kinetic energy changed. Yeah, work can be positive or negative depending on whether you move in the direction you're pushing or if you're moving opposite the direction it pushes. But I won't hold you to all that stuff. But yes, it is a vector. So you can be changing, though, not just kinetic energy. You can change potential energy. Let's start with this one. So potential energy, I told you it's all relative to something. So let's say this is the 0 reference point. This is where there's no gravitational potential energy. Because what's important with gravitational potential energy is the change in position. So if you don't change your position, your height, there's no change in gravitational potential energy. So if I move it up here, what's its gravitational potential energy? mgh. And what is h? That h. That distance. Right. If I let go of it, what will happen? Yeah, I'm hearing good answers. And right back here. So as it goes down, what is it losing? height, mgh, gravitational potential energy is decreasing. Does that energy disappear? It's converted to kinetic energy. You cannot create nor destroy energy. It just changes forms. Total energy is always conserved. It goes somewhere. It has to. So in this case, what's the gravitational potential here? mgh, and h is 0, so it's 0. What's its kinetic energy here? Kinetic, 1/2 mv squared. The velocity is 0. It's not moving at this point, but it's going fast right here, right there. So it's all kinetic right here. And then what's that kinetic convert back into? Potential and kinetic and potential and kinetic and potential. The total stays the same. What is it right here? Both. Right. So, conservation of energy. So, if before you have kinetic and potential before, then that's got to equal the kinetic and the potential after. If no energy was converted to heat or sound from friction or things, then none of it escapes your system. So here, GPE plus 0, you have no kinetic. That's the total. That's the total here, 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 and here. Watch how high it gets. Almost to the same height. Now with time, what do you notice happens? Oh, it's not quite as high anymore. Why? Friction and air resistance. Other forces acting for the same distances as gravity. So they're doing work on the ball also. And where is that energy going? To heat. It does. It warms up the ball and the rails and the air a little bit. But total energy is always conserved. So if you just look at what we call mechanical energy, that's what your book it uses that term. This is mechanical energy, kinetic and gravitational potential energy. Total energy, you got the kinetic and the gravitational to start with, and it's now moving, rolling down the ramp. It still has some height, and what else? The work done by friction. Probably turns it heat. Turns it into the form of energy of heat. So you could actually figure out how much work was done by heat. Work done by friction, converted to heat. If you do this from here, and I don't feel like waiting that long. Okay. To here. See the change in height? If it has, it's all gravitational potential here. And at this point, it's all gravitational potential, correct? You with me? How much did we lose? Lose in quotes. This much, mgh. And where did that convert to? We didn't really lose it. It just left our system. That's the heat. So you could just do the difference. This mechanical energy is always conserved. But if you have these, physicists call them non-conservative forces that cause it to leave your system, then that makes the difference. And you don't get it all back. But it does go somewhere. Total energy has to be conserved. We're about out of time. Let's see. Let's end with just this one, and I'll let you go. This won't even take the 5 minutes. We're going to talk about simple machines. This is an inclined plane. That's a simple machine. You can, when you're trying to move someone, you know, great, you got a piano. Oh. So you can lift it into the truck and do work on it. How much work did I just do? The force times the distance. It's weight mg times the height. How much gravitational potential energy does it now have relative to the table? mgh. Where did it come from? The work I just did. So if you want to know how much work it takes to lift the piano, that height, it's mgh. I've given it that much energy. Well, it's a lot easier, we know, if you put a ramp, you use a ramp and you go like this. You exert a force on it and push it up the length of the ramp to get to the same spot. Now, how much energy does it now have? The same amount. See, it's to the same height, so it has the same exact gravitational potential energy. Where did it come from? The work I did on the ramp. So I did the exact same amount of work using the ramp as I did this way. Do you follow that? I had to have exerted the same amount of energy to get it to the same spot, to have the same gravitational potential energy. Why is this easier then? Yeah, I heard something back there. This is a bigger distance, isn't it? This work, my force was in that direction, so I pushed in this direction over a longer distance. This force is straight up and down over a shorter distance. So, same work done, same energy attained at the end. You can have a big force for a little distance or a little force for a big distance. This is the idea behind simple machines. They don't magically create or magnify energy. People think, oh, they're great, I get mechanical advantage. We'll discuss that more next time. The energy is the same. But they make it easier because you can adjust the distances. Something has to give, though, to keep things conserved. To make it easier, I just have to push for a longer amount of time, a longer distance. Or I can make it hard on myself, but only have to cover a short distance. Same energy required. Questions? Well, have a great day then. Thanks.